Yeah, good morning, dear students. So this is Dr. Vijaya Babu. Today we'll try to discuss about the concepts of voltage division and the current division, which are the most important techniques that are used to analyze the basic electrical circuits. Okay, so this is actually the continuation of the previous lecture. So the previous lecture we had studied about electric potential, voltage, and the current. Okay, so now we'll try to go ahead with the concepts of voltage division and current division, and how the principles of this voltage division and current division will help us in understanding or in analyzing the electrical circuits. So the concept of, first of all, we'll try to go ahead with voltage division principle. So the voltage division, the name itself is saying us, so we are dividing the voltage. Yes or no? So how we are dividing the voltage between different points? So let us take some example here. So let us consider these are the 2 points. This is A to B, the 2 points A and B, and let us assume the potential at this point is 10 volts and the potential at this point is 2 volts. So immediately if I ask me what is the value of the voltage between the points or potential difference across the points A and B, simply we can take this as simply 10 minus 2 volts now. So that is what we call it as 8 volts. So this is the potential difference between the 2 points A and B. Now what I try to do between the same 2 points, so I will try to incorporate one more new point. So that is new point. I try to consider it as something C. Okay. And now if you try to divide the voltage between A and C and C and B, so you can divide as if you want. So let us consider the voltage between these two division is something 6 volts. Then compulsory the voltage division between these 2 points must be what you call as 2 volts. That means the voltage difference between A and B, I have took it as 8 volts. Whereas if you calculate the same difference with a different path, the path what you have followed is something from A to C and C to B. So ACB is a new path what I have took. That means VAB you can measure via the path VACB. That means VAC plus VCB. This is how you can write easily. So that is equal to VAC is 6 volts, whereas this VCB is something 2 volts. So that is equal to 8 volts. So the point what you need to understand is the measurement of potential difference or the voltage between any two distinct points. The voltage between any two distinct points does not depend on the path. Okay, it does not depend upon the path what you have considered. This is a little bit example about some sort of voltage division, that is 6 volts and the 2 volts division, and the total end to end points, that is A to B, the voltage difference is something it has 8 volts. Okay, so now I'll try to go ahead the same division. I will usually it is not possible to divide the voltage like this, so it's better if you try to go ahead by if you go with the same division using resistors. So the same concept now I will try to explain using resistors. So let us consider two resistors. This is R1, R2, R1, R2. Okay, now the overall voltage between the points A and B. Okay, let us consider it as V. The overall voltage between the points A and B, we'll try to consider it as V. Then, okay, So now if I try to consider some extra point C here, and I'll try to calculate the voltage across the resistor R1 as V1. We'll have to consider the voltage across R2 as V2. Now simply we can write here a simple statement: V is exactly equal to V1 plus V2. So the overall voltage between the points A and B is exactly equal to the sum of two individual voltages, that is from A to C, VAC, and C to B, that is VCB. So VAC plus VCB is directly equal to VAB. So what I have shown here. Okay, so now this is some equation what I have written in terms of voltages. So if I try to go ahead with the individual voltages, how to calculate, how the voltage division happens. See here, the voltage V1 is something like this. It is equal to the same resistance divided by total resistance, that R1 and R2 are in series na, because the voltage division will happen only in the series connection. That also you have to understand. So V1 is equal to R1 by R1 plus R2 into total voltage V, whereas the value of V2, another voltage, the value of V2 is simply given as the voltage is across R2 na, so that is R2 divided by R1 plus R2 into total applied voltage, that is equal to V. Okay, so this is how you have to understand the voltage division principle. So voltage division principle, so usually I will try to draw another circuit which is exactly equal to the voltage division. I think in your textbooks you might be seeing this one. So this is something like V, and this V is acting across the series combination of two resistors R1 and R2, something like this. And if you ask me to denote the value of V1, so this is V1 and this value is equal to V2. So here both are looking something different, but they are same. So here in the circuit, voltage V is acting across the series combination of R1 and R2. Here, this is also the voltage across the series combination of R1 and R2. So both are almost same. So extra I have used here a battery. The battery meaning is that this will give always a potential difference of V volts across the series combination of R1 and R2. So this is how we have to understand the concept of voltage division. So I'll try to go ahead in explaining the same concept by taking a practical example. A small electrical circuits I'll try to consider. So let us consider, so this is a 10 volts battery which is connected across the two resistors, something like this. And this value, so I'll try to give it as 2 ohms, and this value I try to give it as 10 ohms. Then if you ask me the voltage across the 2 ohms resistor is V1 and the voltage across the 8 ohm resistor is V2. If you ask me to calculate V1 and V2, so I'll try to directly go ahead with the voltage division principle. So immediately you can ask me, so there are a lot of KVL is there, KCL is there, okay, Ohm's law is there. There are a lot of methods are there. Why we need to strictly use this voltage division principle in this particular example? The meaning is that to apply the voltage division principle, it is not required to calculate any current in this loop. It is not required to calculate any current. It is not required to calculate any current in the 2 ohm resistor. It is not required to calculate the current in the 8 ohm resistor. It is not required to calculate the current coming out of the battery. Okay, so that is the best advantage of the voltage division principle. So the current measurement is not at all required. Directly using voltage division, I can consider the voltage V1 is exactly equal to, the formula is saying what? Same resistance, right? Divided by total resistance 2 plus 8 into total applied voltage, that is 10. So V1 value is simply 2 by 10 into 10, so exactly equal to 2 volts. Similarly, the value of V2 is simply same resistance by total resistance into total applied voltage, so 8 volts. So finally I got V1 is equal to 2 volts and V2 is equal to 8 volts. So this is how we need to calculate the values of V1 and V2 using the voltage division principle without calculation of any currents in the loop. Okay, so that is the advantage of the voltage division principle. Now I'll try to go ahead with the concepts of current division. So the current division, when the current division will happen, the voltage division when it was happened when there are series combination of two resistors. Now the current division will happen when there are a parallel connection of two resistors. That means the current division will happen something like this. Two resistors R1 and R2, they are connected in parallel, and let us assume a net current of I amperes is flowing through the combination of parallel combination of both R1 and R2. So in this scenario, how will you calculate the current through the individual resistors? That means this is I1 and this is I2. So here the current division will help us directly to calculate the values of I1 and I2. So however, the value of I1 is simply given as, so it is always the opposite resistance, that is the value is R2 divided by R1 plus R2 whole multiplied with total entering current in this parallel combination. What is the total entering current in the parallel combination? That is I. Similarly, the value of I2 is equal to R1 divided by R1 plus R2 into I. So this is how we can understand the values of branch currents, that is I1 as well as I2. So the advantage of this method, once again, what I want to tell you is, so the advantage of this method is it is not required to calculate. So it is not required to calculate any voltages. Simple. If you understand the beauty of voltage division principle, it is not required to calculate the value of currents. Similarly, if you try to see the beauty of this current division principle, so it is not required to calculate any voltages. So that is straightforward advantage of this current division principle. So I'll try to go ahead now by taking a small practical example for your convenience. So let us consider it is a current source, so which is trying to produce always 8 amperes, and this is 2 ohm and this is 6 ohm resistors connected in parallel. Now I'll try to calculate the value of I1 and I2 using current division principle. So using current division principle, so what is the value of I1? I1 is simply opposite resistance, na? That is 6 divided by total resistance. 6 plus 2 into total entering current. What is total entering current? 8 amperes. So 6 by 8 into 8, that is equal to 6 amperes. Whereas the value of I2, opposite resistance, 2 divided by 6 plus 2 into 8 amperes. So 2 by 8 into 8 amperes. So this is equal to 2 amperes. So finally I got the values of I1 as 6 amperes and the value of I2 as 2 amperes. Okay, so this is how we can calculate the values of I1 and I2 using the current division principle. Okay, so now if you ask me to extend these things for the series combination of three resistors, so let's assume this is something like 12 volts battery. It's connected across 2 ohms. So then it is 4 ohms, 6 ohms, something like this. Now, if you ask me to calculate voltage drops across all the resistors, that means if you ask me to calculate V1, V2, and V3 across 2 ohms, 4 ohms, and 6 ohms, straightforward using voltage division V1 same resistance divided by total resistance 2 plus 4 plus 6 into total applied voltage 12. So which is equal to 2 by 12 into 12, which is equal to 2 volts. So V1 is equal to 2 volts. So V2 is equal to same resistance by total resistance into total voltage. So 4 volts. Similarly, V3 is equal to same resistance by total resistance into total. Even you can not only the voltage is shared among the two resistors, the same thing will happen in terms of the same sharing will happen in terms of the series combination of three resistors as well. Okay, so now I'll try to go ahead with the same concept of current division. Okay, so same I'll try to give it as 10 amperes. So let us assume it is a parallel combination of 2 ohms, 4 ohms, 3 ohms. Now using the current division, easily you can calculate the value of I1, I2 and I3. So how will you calculate the value of I1? I1 is nothing but opposite resistance. Opposite means there are the combination of both 4 and 3. Na? So what is the net combination? So 4 into 3 divided by 4 plus 3. This is opposite resistance, na? Because the two are in parallel. So 12 by 7. Okay. Whole divided by the total resistance 2 plus 4 plus 3 into total entering current, that is 10 amperes. Okay, so how will you calculate this? So 12 by 7 whole divided by 10. Okay, so multiplied with what you call it as 10. So from this you can directly write it as 12 by 7 amperes. Okay, similarly you can calculate the value of I2. So I2 is exactly equal to opposite parallel combination. That means 2 into 3 divided by 2 plus 3 divided by 2 plus 4 plus 3 into 10. Total current is 10. Na? 6 by how much? 5 amperes. Similarly, the value of I3 can be calculated using current division. So opposite resistance. Opposite resistance is what? Parallel combination of 2 and 4. Na? So 2 into 4 divided by 2 plus 4 whole divided by, this is 10 into 10. So that means it is something like 8 by 6 amperes. So this is how you can calculate the values of I1, I2, I3 using current division principle. So the advantage of the current division is what I said. So it is not required to calculate the voltage across the resistors. Okay, to calculate the currents. Similarly, the advantage of voltage division is nothing but it is not required to understand anything about the current. So this is the main advantage of both voltage division principle and the current division principle. Okay, so thank you for giving this opportunity so to discuss this concept. So in the next lecture, we'll try to go ahead with the concepts of KVL and KCL. Thank you. This is Dr. E. Vijaya Babu signing off.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.